Okay, let's continue on in this video and talk more about the power triangle. As we discussed previously, you can show the components of complex power, which is S, in a right triangle that we call the power triangle. Here I wrote one of the expressions for P average, I squared R, and then here on the opposite side of the right triangle I wrote an expression for reactive power, I squared X. Now, we can factor out the I squared and show that complex power is just equal to current squared times Z, right? Because R plus or minus JX is just impedance. So you see that's the hypotenuse of this right triangle is complex power, and one expression for complex power is that it's current squared times impedance. So if you look at this, you can see that the power triangle is just the impedance triangle scaled by I squared, just scaled by a factor, right? Because if we were to divide each side of our power triangle by I squared, we would just get Z X R. We just get the impedance triangle. So this is a proof of what I mentioned in a previous video, that the theta, right, our power angle, is just equal to theta Z, the phase angle of the impedance. So you can see that pictorially here, since these are the same triangles, they're just scaled versions of each other, so these angles are the same. Here's theta Z here. Okay, so this is really important to realize, especially when we get further along, we start doing some problems that these two angles are identical. Okay, well, we can also write that each one of these powers in terms of voltage, because we know that current through a resistor is just V over R. So I can substitute in for P average, I can substitute in V over R for I, right? So I'll have V squared over R squared times R, right? And that R cancels out one of these R's. So P average is also equal to V squared over R. Likewise, same reasoning, you can write the current for the reactance as the voltage across the reactance divided by the reactance. So Q, reactive power, is also equal to voltage squared over X, and S, the complex power, is equal to V squared over Z. So one other thing I wanted to mention about S, as I'm thinking about it here, is that, you know, again, S is a made-up power. We make it up and we give it the definition that S equals V times complex conjugate of I. You know, we give this made-up power this definition so it leads to this convenient result, so we can express these quantities in a right triangle. And as I mentioned earlier, P average and Q are powers that are tangible, that you can actually measure, but S is something that, you know, it's not, you can't measure it directly, but we think of S as being the total power to an impedance. Okay, so S is thought of as the total amount, and then that total amount is broken up into these you know, tangible quantities, these measurable quantities, P average and Q. Well, we're not done yet with the various powers that we have, because there's another power used in AC circuits that's called apparent power. Okay, and apparent power is just the magnitude of S. Okay, so it's just the magnitude of complex power, and it's just equal to V times I. Okay, has units of volt amperes, just like complex power does. In fact, let's go back and just quickly review the units of powers of our AC powers. See, complex power and also apparent power, have the same units VAs, right? Because apparent power is just the magnitude of complex power, so it has the same units. Reactive power from a previous video, remember that its units are VARs, and then P average has units of watts, just like DC power. Okay, so that's just a quick little review of the units for the various powers that we have. Now, another or a couple other expressions that we have for P average and Q. Okay, we already have about at least 3 equations for P average, but another one for P average that just comes from your basic trig is that since the hypotenuse here is apparent power, P average is just equal to apparent power times cosine theta, which is the same as apparent power times power factor. Okay, and we're going to talk about more about power factor being cosine theta at the end of this video. And then likewise, Q from basic trig is just apparent power sine the angle. Alright, so there's a couple of other expressions that we often use in AC power problems. Well, that brings us to why we have this definition here that power factor equals cosine theta. Okay, to explain that, I have a handout, okay, right here, that shows the use of defining power factor as cosine theta. And as you can see here, if we have a power factor of 1, that means the angle, the theta of our power triangle is 0, right? Because cosine 0 is 1. So you see what that means is that we don't have a power triangle at all, that since the theta is 0, well, P average and complex power are going to be the same value. Now, if you have a power factor that's close to 1, like 0.9 something, well, that means that this angle of our power triangle is a very small angle. So it could either be a very small positive angle or a very small negative angle. And you see, this tells us that most of the total power is being absorbed, okay, because you're going to have a larger real component, P average, than imaginary component, Q. Now, the way we distinguish between a small positive angle and a small negative angle is with these terms lagging and leading. If it's a positive angle, which is inductive, okay, remembering again that this angle theta is the same as theta z. So if you have a positive power triangle angle, that means you have a positive theta z, which is inductive. So if you have an inductive impedance with a positive angle, we call that a lagging power factor. Okay, so this would be a power factor close to 1 that's lagging. If it's capacitive, well, you'd have a negative angle here, and we refer to that as leading. The opposite end of the spectrum is when you have a power factor near 0, because when your power factor is near 0, this angle is going to be large, right? It's going to be close to 90 degrees. So now most of your total power is being exchanged because most of it is reactive power, and there's only a small amount that's absorbed. That's the real power, or P average. So you see, the purpose of defining power factor as being the cosine of the angle of the power triangle is just so that when you hear a number between 0 and 1, well, a mental image of the power triangle should pop into your head. It's very similar to when we use Q in frequency response, right? That quality of a bandpass filter is inversely proportional to bandwidth. So once you understand that relationship, just hearing a number, a mental image of the frequency response curve should pop up into your head. Well, it's the same sort of thing here, that we define power factor this way because once you have an understanding of what that angle is, well, now if you hear a power factor close to 1, one of these angles is, or one of these triangles is going to pop up into your head, depending on whether the theta is positive or negative, depending whether you have lagging or leading. And same thing here on the other end of the spectrum, or anywhere in between. If you had a power triangle that had equal, opposite, and adjacent sides, so your angle is 45 degrees, well, cosine 45 degrees, as you know, is 0.707. So a power factor of 0.707 means that you have an impedance that has an equal amount of absorbed power to how much is being exchanged. Okay, so that's the whole idea behind power factors. So as you saw here, it took 3 videos really to go over all the different definitions and fundamentals of AC power. And in the next few videos, we're going to start doing AC power problems.